When calculating voltage drop for panel feeders, it's crucial to consider potential future load expansion. This ensures that the feeders have sufficient capacity to handle increased load demands and maintain acceptable voltage drop levels. There are generally two approaches to accounting for future load expansion when calculating voltage drop. Firstly, use the maximum connected load. Utilize the maximum connected load of the panel, even if it is significantly higher than the current load, to ensure adequate voltage drop performance for future expansion. Secondly, apply a load growth factor. Multiply the current connected load by a load growth factor, typically 20% to 30%, to estimate the potential future load. Let's consider an example. Suppose the panel has a rating of 100 amps and the upstream circuit breaker is rated for 100 amps as well. The current connected load is 50 amps. Using method 1, maximum connected load. Use 100 amps, the panel rating, as the connected load, even though the current load is only 50 amps. Using method 2, load growth factor. If the current connected load is 50 amps and you apply a load growth factor of 20%, the future estimated connected load is 50 amps multiplied by 1.2, which equals 60 amps. Once the connected load is determined, calculate the voltage drop using the following general formula. Voltage drop equals the connected load divided by the circuit conductor ampacity multiplied by the circuit length, and then multiplied by the resistance per unit length. Note that the circuit conductor ampacity is typically equal to the circuit breaker rating. Circuit length is the distance from the upstream of a current device to the panel. Resistance per unit length is provided by the conductor manufacturer. Let's look at the different components of the voltage drop equation in detail. The term connected load refers to the total amount of electrical current, measured in amps, that is expected to be drawn by all the devices and equipment connected to the circuit. This is a critical factor because a higher connected load will naturally result in a greater voltage drop along the circuit. The circuit conductor ampacity represents the maximum amount of current, measured in amps, that the circuit conductors, or wires, are rated to safely carry. This rating is determined by factors such as the wire gauge, insulation type, and insulation conditions. Using conductors with a higher ampacity can reduce voltage drop, as they offer less resistance to the flow of current. The circuit length is the physical distance, typically measured in feet or meters, from the power source, such as the circuit breaker or transformer, to the load. The longer the circuit, the greater the voltage drop will be, as the current has to travel a longer distance through the conductors. The resistance per unit length is a characteristic of the conductor material, typically measured in ohms per foot or ohms per meter. It represents the opposition to the flow of current for a specific length of the conductor. Different materials, such as copper and aluminum, have different resistivity values, with copper generally having lower resistance than aluminum. Also, thicker wires have lower resistance per unit length. The National Electrical Code, or NEC, provides guidelines for voltage drop in branch circuits and feeders in sections 210.19a on and FBN number 4, and 215.2 A3 and FBN number 2, respectively. It recommends that the voltage drop should not exceed 3% in branch circuits and 5% in feeders, resulting in a maximum total voltage drop of 5% when combining branch circuits and feeders. These are recommendations, not hard requirements. There's no guarantee the authority having jurisdiction, also known as the AHJ, will require adherence to these recommendations. These recommendations help ensure efficient operation and prevent equipment malfunction. High voltage drop can cause lights to dim, motors to overheat, and electronic devices to malfunction. By keeping the voltage drop within acceptable limits, you can maintain the performance and longevity of electrical equipment. Voltage drop calculations are essential for selecting the appropriate wire size for electrical circuits. If the voltage drop is too high for a given wire size, you need to increase the wire size to reduce the resistance and lower the voltage drop. Larger wires have a lower resistance per unit length, which reduces voltage drop over long distances. When selecting conductors for a project, begin by determining the design current of the circuit. This is the maximum amount of current that the circuit is expected to carry under normal operating conditions. Use the connected load and apply any applicable demand factors as outlined in the NEC. Next, determine the minimum conductor size required to carry the design current in accordance with NEC Table 310.16 or other applicable tables. This table provides ampacity ratings for various conductor sizes based on their insulation type and installation conditions. Be sure to apply any necessary correction factors for ambient temperature or the number of conductors in a raceway. Once you have determined the minimum conductor size based on ampacity, calculate the voltage drop for the circuit using the voltage drop formula we discussed earlier. Use the appropriate values for circuit length, connected load, and conductor resistance. If the calculated voltage drop exceeds the recommended limits, increase the conductor size until the voltage drop is within acceptable limits. Remember that voltage drop is directly proportional to the conductor resistance. So, increasing the conductor size will reduce the resistance and lower the voltage drop. In some cases, it may be necessary to use multiple parallel conductors to reduce voltage drop, especially for long circuits with high current loads. When using parallel conductors, ensure that they are properly sized and installed in accordance with NEC requirements. You must also ensure that you follow NEC Section 310.10h. There are many online voltage drop calculators available that can simplify the process of calculating voltage drop. These calculators typically require you to input the circuit parameters such as voltage, current, conductor size, circuit length, and conductor material. The calculator will then calculate the voltage drop and display the results. Some calculators also provide recommendations for conductor size based on the calculated voltage drop. When using a voltage drop calculator, make sure that you are using accurate and reliable data for the circuit parameters. Incorrect data can lead to inaccurate results and potentially unsafe installations. Always double-check the calculator's results with your own calculations to ensure accuracy. Also be sure to select the right conductor type based on the application and the calculator's requirement. Some electrical installations may require the use of specialized conductors to minimize voltage drop. For example, conductors with lower resistance materials, such as copper, can be used to reduce voltage drop over long distances. Additionally, conductors with larger cross-sectional areas can be used to increase ampacity and reduce voltage drop. In some cases, it may be necessary to use voltage drop compensation techniques to maintain voltage levels within acceptable limits. Voltage drop compensation involves increasing the voltage at the source to offset the voltage drop along the circuit. This can be achieved through the use of transformers with tap changers or automatic voltage regulators. Another technique is to use active voltage regulation devices, which automatically adjust the voltage to compensate for voltage drop. These devices are commonly used in critical applications where voltage stability is essential, such as data centers and hospitals. Consider the impact of harmonics on voltage drop. Harmonics are distortions in the electrical waveform that can increase the effective current in a circuit, leading to higher voltage drop. If harmonics are present, it is important to use a harmonic mitigation technique, such as installing harmonic filters or using transformers designed to withstand harmonic currents. Also consider the effects of temperature on voltage drop calculations. Conductor resistance increases with temperature, which can lead to higher voltage drop. Be sure to use appropriate temperature correction factors when calculating voltage drop, especially in high temperature environments. NEC Table 310.15 specifies the temperature correction factors to use based on the conductor's insulation type and ambient temperature. Proper documentation of voltage drop calculations is essential for ensuring compliance with electrical codes and standards. Keep a record of all calculations, including the circuit parameters, conductor size, voltage drop, and any assumptions made. This documentation can be useful for future reference and for troubleshooting any voltage drop related issues. Review the calculations with a qualified electrical engineer or inspector to ensure accuracy and compliance.